To leave Earth, we have to generate an explosive amount of upward force. During the recent Artemis mission to the Moon, the launch required burning through massive tanks of chemical fuel just to break the grip of Earth's gravity. This creates a vicious cycle of weight. Moving anything into orbit requires hauling thousands of gallons of propellant, but all that liquid is heavy, meaning engineers have to add even more fuel simply to lift the weight of the fuel itself off the launch pad. This chart shows the exponential ratio of fuel weight to payload weight for traditional rockets. By the time a ship reaches orbit, only a tiny fraction of its total mass is dedicated to cargo or crew. Because the ship burned almost everything to get there, its maximum speed is strictly capped, turning a trip to Mars into a multi-month crawl. Combustion fire is effective in the dense environment of our atmosphere. But the moment a ship enters the frictionless vacuum of space, relying on heavy, exhaust-dependent chemical reactions becomes a liability. If we plan to build outposts on the Moon and consistently transport humans to Mars, the math suggests we need to move past combustion the moment we clear Earth's atmosphere. In an industrial estate in southern England, engineers at Pulsar are testing an alternative. They are building an engine designed specifically to operate in the vacuum of space. Their concept is called the Sunbird rocket. It relies on a two-stage system. The ship leaves the ground using traditional combustion fire, but once it reaches the vacuum of space, it switches to nuclear propulsion. The system relies on nuclear fission. This is the process of taking the nuclei of two distinct atoms and forcing them to collide. The impact releases an extreme, disproportionate amount of energy. It is the same atomic reaction that acts as the primary power source for the sun. Inside the Sunbird engine, special atoms are stored and then heated to such extreme temperatures that they bypass the solid, liquid, and gas phases of matter. They transition into a fourth state of matter called plasma, a soup made up of highly charged ions and electrons. Mastering this volatile plasma produces an exhaust speed that standard chemical fire cannot achieve. To test this spacebound engine on Earth, engineers use high-powered pumps to suck the air out of a warehouse chamber, mimicking a vacuum. Inside this chamber, the team recently achieved first plasma. Under immense pressure, the engineers successfully ignited the fusion process, creating the intensely hot atomic soup within a controlled environment. Plasma destroys physical walls, so the engine uses powerful electromagnets. These fields wrap tightly around the plasma, holding it steady. To convert this into movement, the fields squeeze tighter at one end, forcing the plasma out a narrow exhaust, creating massive forward thrust. The environment inside the chamber is intensely hostile. During the test, the energy radiating from the plasma destroyed the sensor of a GoPro camera placed inside to film the reaction. Holding this high-pressure plasma steady within the exhaust structure demonstrates that the mechanics of a fusion rocket are ready for larger-scale testing. Rocket efficiency is often measured by specific impulse. The Sunbird engine is currently projecting a rating of about 13,000 seconds. When applied to a deep space trajectory, that level of efficiency would cut the travel time to Mars completely in half. While Pulsar focuses on space, the UK Atomic Energy Authority investigates similar physics for terrestrial use, with plans to have fusion on the national power grid by the 2040s. This is part of a broader effort in deep space propulsion. American companies like Avalanche Energy and Princeton Satellite Systems are developing their own fusion engines. These projects coincide with international plans to build permanent, populated bases on the lunar surface. To support those ambitions, we need propulsion that can handle the distances. Seeing a plasma plume light up in a vacuum chamber demonstrates the technology we need as we migrate further into the solar system.